Good morning, ninth class students. Today's lesson is the elements of geometry, part 2. In part 1, we learned the history of geometry and the contribution of Euclid, how Euclid defined point, line, and plane. Later, why mathematicians considered point, line, and plane are undefined terms. Now, in this lesson, we will go through Euclid's axioms and postulates. Euclid assumed some properties which need no proofs. These assumptions are self-evident truths. He divided them into two types. They are axioms and postulates. Dear students, axioms and postulates both are same. Postulates are used specific to geometry and axioms are used throughout mathematics and not specifically linked to geometry. That's all. Axioms or postulates are statements which are self-evident or assumed to be true within context of a particular mathematical system. Example, the whole is always greater than the parts. It is a self-evident fact and does not require any proof. The axioms are foundation stones on which the structure of geometry is developed. The axioms arise in different situations. Now, let us examine some Euclid's axioms. Things which are equal to the same thing are equal to one another. That means if A is equal to C and B is equal to C, then A is equal to B. Here A, B and C are same kind of things. One more axiom. If equals are added to equals, the whole are equal. That means if A is equal to B and C is equal to D, then A plus C is equal to B plus D. Also, A is equal to B, then this implies A plus C is equal to B plus C. If equals are subtracted from equals, the remainders are equal. Things which coincide with one another are equal to one another. One more axiom. The whole is greater than the part. Next one. Things which are half of the same things are equal to one another. Things which are double of the same things are equal to one another. That means if A is equal to half of the B and C is equal to half of the B, then A is equal to C. Similarly, if A is equal to twice of the B and C is equal to twice of the B, then A is equal to C. These common notations refer to magnitude of same kind. Now, we are going through Euclid's 5 postulates. The first postulate is there is unique line that passes through the given two distinct points. That means if two distinct points are there, we can draw only one line through those 2 points. And second postulate, a line segment can be extended on either side from a straight line. Euclid's third postulate, we can describe a circle with any center and radius. Euclid's fourth postulate, all right angles are equal to one another. Now we are going into Euclid's fifth postulate. It is very important and critical. If a straight line falling on two straight lines makes the interior angles on the same side of it taken together is less than two right angles, then the two straight lines, if produced infinitely, meet on that side on which sum of angles is less than two right angles. That means, for example, the line PQ in figure falls on line AB and CD such that the sum of the interior angles 1 and 2 is less than 180 degrees on the left side of PQ. Therefore, the lines AB and CD will eventually intersect on the left side of PQ. The fifth postulate has acquired much importance as many mathematicians, including Euclid, were convinced that the fifth postulate is theorem. Consequently, for 2000 years, mathematicians tried to prove fifth postulate. Dear students, now we are learning some postulates which are equivalent to Euclid's fifth postulate. John Playfair's postulate. Through a point not on given line, exactly one parallel line may be drawn to the given line. It is also called Playfair postulate. Let L be a line and P be a point not on L. So, through P, there exists only one line parallel to L. It is proposed by Playfair. Now, Legender's proposal, which is equivalent to Euclid's fifth postulate. The sum of angles of any triangle is constant and is equal to two right angles. Now, Posidonius' proposal, which is equivalent to Euclid's fifth postulate. Posidonius said, there exists a pair of lines everywhere equidistant from one another. Now, Proclus' proposal. If a straight line intersects any one of two parallel lines, then it will intersect the other also. One more statement by Proclus, which is equals to Euclid's fifth postulate. Straight lines parallel to the same straight line are parallel to one another. After stating these five postulates, Euclid used them to prove many more results by applying deductive reasoning, and statements that were proven are called propositions or theorems. Statements which are neither proved nor disproved are called conjectures or hypotheses. Example, Goldbach conjecture. Every number greater than 4 can be written as the sum of two primes. A conjecture that is proved to be true is called theorem. A theorem is proved by logical chain of steps. The steps used in proving a theorem are: first step, proposition, that means the statement itself. Second step, diagram. Third step, given. Fourth step, required to prove, that is also called RTP. Fifth one, construction if needed. Sixth one is proof. Euclid deducted 465 propositions. That means Euclid proved 465 theorems. Let us go through a proposition. Two distinct lines cannot have more than one point in common. What is given here? Two lines, say L and M. RTP, they have only one point in common. Proof. Let us assume that two lines intersect in two distinct points, say A and B. Now we have two lines passing through A and B. This assumption contradicts with Euclid's axiom that only one line can pass through two distinct points. This contradiction arose due to our assumption that two lines can pass through two distinct points. So we can conclude that two distinct lines cannot have more than one point in common. Let us solve a small question. In the adjacent figure, if angle A is equal to angle 3, angle 2 is equal to angle 4 and angle 3 is equal to angle 4, write the relation between angle 1 and angle 2 using an Euclid's postulate. As Euclid's axiom says, things are equal to the same thing are equal to one another. So, angle 1 equals to angle 3 is given and angle 3 equals to angle 4 is given. Hence, we can say that angle 1 equals to angle 4. Now, angle 1 equals to angle 4 and given is angle 2 equals to angle 4. Hence, we can conclude angle 1 equals to angle 2. What is the shape of the earth? It is not flat. It is not plane. The shape of the earth is sphere. Observe the lines. The lines are not straight. They are part of great circle. All are intersecting lines. That means there are no parallel lines. This geometry is called spherical geometry or elliptical geometry. It is a kind of non-Euclidean geometry. In it, sum of angles in a triangle is greater than 180 degrees. Riemann and Klein contributed a lot in developing elliptical or spherical geometry. In spherical geometry, perimeter of a circle is less than 2 pi r. Dear students, observe the horse saddle shape. It is called hyperbolic paraboloid shape. By observing the lines, we can say we can draw infinite parallel lines to a line from the point which is not on the line. This geometry is called hyperbolic geometry. It is also one kind of non-Euclidean geometry. In it, the sum of angles in a triangle is less than 180 degrees and the perimeter of circle is greater than 2 pi r. Lebowski, Gauss and Klein contributed a lot in developing hyperbolic geometry. We examined here three kinds of geometries. In it, Euclid geometry says sum of angles in a triangle is 180 degrees. Spherical geometry says sum of angles in a triangle is greater than 180. In hyperbolic geometry, sum of angles in a triangle is less than 180. In Euclid geometry, perimeter of a circle is 2 pi r, and in spherical geometry, perimeter of a circle is less than 2 pi r. In hyperbolic geometry, perimeter of a circle is greater than 2 pi r. And in Euclid's geometry, parallel lines are parallel itself. And in spherical geometry, parallel lines are convergent. And in hyperbolic geometry, parallel lines are divergent. So which geometry is correct? Dear students, all are correct. And one more thing, all are self-sufficient. That means spherical geometry not dependent on Euclid geometry, at the same time not dependent on hyperbolic geometry. Similarly, the principles of hyperbolic geometry not depend on spherical or Euclid geometry. All are self-sufficient and all are correct also. Then which geometry is useful? When we study about our universe, we use hyperbolic geometry. When we study about our earth, we use spherical geometry. In construction of bridges, buildings, roads, and in measure of agricultural fields, etc., we use Euclidean geometry. The key points are listed here. Pause the video and note down the key points. Now it's time for homework. Dear students, solve these questions. If you have any doubts, you can call me without hesitation. Thank you for listening.